Okay, welcome to day 5. We're going to graph logarithmic functions, and we're going to talk about limits a little bit. First part of today is be graphing log functions, and we're going to relate them to what we did before with exponentials. So here are two functions. F of x equals 2 raised to the x, and g of x is log base 2 of x. They both have the same base of 2. So what's the relationship? They are inverses. Why they're inverses? Well, this first one is an exponential. This second function is a logarithmic. And the idea is that these two functions will undo each other. And that's what we've been working on with solving equations. So what happens with the graphs? They have what we call a reflective symmetry over the line y equals x. So that diagonal line y equals x is going to be where it's going to be symmetric, or we say we switch x and y values. That's how we do inverses on a graph. We switch x's and y values. So we're going to graph both these functions. First, we're going to do the exponential functions of 2 raised to the x. I'm going to plug in these numbers. I don't care which order you go to. I could start here. 2 squared is 4. 2 to the first is 2. 2 to the 0 is 1. 2 to the negative 1 is 1 over 2. And 2 to the negative 2 is 1/4. I'm going to plot all these. Excuse me, it's a bad graph. I can't even see my eraser. 0, 1. 1, 2, 2, 4. Technically it would be 3, 8. I'm going to put it there just to help me guide me. And then there's a half. And the graph looks something like this to the best of my ability. And this is f of x is equal to 2 raised to the x. Nice exponential function. Left side levels off. Right side goes up to infinity. So now when I want to do its inverse, I'm going to switch x and y's. And to do all that, I'll do it in pink. I'm going to do that graph here. So instead of negative 2, 1/4, it'll be 1/4, negative 2. 1/2, negative 1. 1, 0, 2, 1, 4, 2. I'm going to graph these points on this graph. 1, 0, 2, 1, 4, 2. If that was 3, 8, this would be 8, 3. And then 1/2, negative 1. And I have this graph kind of looks like this. And this graph in pink is g of x equals log base 2 of x. And if you can see, they are inverses of each other. And even better yet, I could draw this diagonal line . Here's the diagonal line, y equals x, and you can see they are mirror images over that diagonal line. And this is what happens. So let's look at the characteristics. First, let's look at the characteristics of the blue graph, the exponential. The domain is all real numbers. The range is 0 to infinity. There is an asymptote. There is a horizontal asymptote of y equals 0. X-intercept, there is no x-intercept on that blue graph. The y-intercept is 0, 1. And if I want to name another point on that graph, I could say 1, 2 or 2, 4. There's more than that, but that's good enough. Well, let's do the pink graph. Well, let's see. My domain now is 0 to infinity. Seems something switched. My range is all real numbers. I don't have a horizontal asymptote. I have a vertical asymptote of x equals 0. My x-intercept is 1, 0. My y-intercept, there is none. And my points are now 2, 1. And 4, 2 are other points on this graph. And if you notice, I basically had x's and y switched. Y equals 0, now it's x equals 0. 0, 1, now it's 1, 0. 1, 2, 2, 4, 2, 1, 4, 2. We are switching x's and y's, and that's how we do an inverse. So let's talk about what a graph looks like in general for a log graph. That little b is the base. So every graph is going to look like this. This is what we did on the previous page. The graph is going to look like this curly graph, like this. And this point that it goes through right here, or is always going to be the point 1, 0. This next point on the graph will be b, 1, whatever the base is. If the base is 5, it's going to be 5, 1. If the base is 10, it's 10, 1. And this the next point over here will be b squared, 2. We'll do an example, but whatever the base is, and that will give me 3 points. So you technically only need 2 points, but 3 points isn't bad. The domain, well, first of all, we have a vertical asymptote. Right down the middle here is a vertical asymptote of x equals 0. So there's no left part of this graph. So my vertical asymptote is x equals 0. My domain is 0 to infinity. My range is all real numbers. My x-intercept is 1, 0. My y-intercept, there is none. Another point on the graph would be base, 1, or base squared, 2, base cubed, 3, or so on and so forth. And then over here, we're looking at the right side of the graph. If we go farther right, this graph is going up forever. It goes up to infinity. It goes up very slowly to infinity, but it does grow forever to infinity. Exponential graphs are the fastest growing functions, and logarithm graphs are the slowest growing functions. They do grow forever. They do not level off. And then over here, it says 0 with a little plus sign. So on the right side of the graph, next to 0, this graph is going down to negative infinity. So the basic graph will always look like this. If you're unsure, you can always do an exponential b to the x and just switch x's and y's. But for me, we're going to do these enough. These are the 2 or 3 points I should know. 1, 0, base, 1. If you want to do another point, b squared, 2. So just like we did with exponentials, we have the 3 letters a, c, and d. We're avoiding b because that was the base. So what does a do to the graph? Well, a is a vertical stretch or compression. And if a is equal to a negative, it flips the x-axis. But in general, my a value is going to change y, so I just do a times the y values. C is going to be left or right by the opposite of c. So plus 5 would be left 5 and vice versa. But it also changes my domain a little bit. What happens is that I get a VA. My VA is always x equals the opposite of c, and my domain is always negative c to infinity. So moving a graph left and right, in this case, also moves the vertical asymptote left or right. And then finally, the d is up or down by d. That's the easiest one whatsoever. So we're going to do an example here. I see I have 3 letters. I have an A, I have a C, I have a D, and I'm going to figure out how I can draw this graph. What first I should always do is draw the parent. So the parent for this graph is y equals log base 3 of x. Because it's base 3, so if you're not unsure how to find points on this graph, just do 3 to the x. Well, 3 to the x, if you plugged in 0, 1, and 2, your answers would be 1, 3, and 9. And you see here, I'm just switching x's and y's. So that's how I got. So right now I have 1, 0, 3, 1, and 9, 2 are my 3 points on this graph. And this graph right here is log base 3 of x. That's the parent graph. What are the transformations I see? Well, let's see. My a value is going to flip the x and vertically stretch by 3, or better yet, negative 3 times the y values. My c value is going to go left 4, and my d value is going to go down 2. not only is it left 4, x equals negative 4 is going to be the VA. So I'm going to mark that to begin with. Here's my VA of x equals negative 4. And now let's do the points. I'll do it in blue. So right here at 1, 0, multiplied by negative 3 still does at 1, 0 because I'm multiplying y values, and left 4, 1, 2, 3, 4, down 2, gives me a point right here. And that point right now is negative 3, negative 2. This point right here, I'm going to multiply by negative 3, so I could flip it and multiply by 3, and now it's at y is negative 3. I could go 1, 2, 3, 4, 1, 2. Here's my next point, which is negative 1, negative 5. And if I want to do a third point, I don't have to. I could draw the graph now, but I can multiply this by negative 3 by flipping it. Negative 2 times 3, negative 6. Left 4, 1, 2, 3, 4, 1, 2. And that point would be at 5, negative 8. And it's still going to be that curly graph, but now it's flipped upside down. So now it looks like this. And there's that graph. My domain is negative 4 to infinity from the vertical asymptote over. My range is all real numbers. I'm going to move this graph up a little bit so I can see more of this. I'm going to come back to the x and y intercept because those are going to be some work. The right side, look at this right side. It goes down forever. It goes down to negative infinity. And as x gets closer to negative 4 from the right side, is going up to positive infinity. Now I have to do some math work. When I want to find an x-intercept, I have to use y equals 0. And when I want to find a y-intercept, I use x equals 0. Well, I could do this one first. So I plug in 0 into this equation that's on the top here. I get y equals negative 3 log base 4, plugging in 0, log base 4, I'm sorry, log base 3, all 4, minus 2, and I went to my calculator, and I typed this in my calculator, and I got the number that was about equal to negative 5.786. So 0, negative 5.786 is the y-intercept. Now the hard part is the x-intercept. I have to make my equation equal to 0. Negative 3 log base 3 x plus 4 minus 2. I'm going to add 2 to the other side. 2 equals negative 3 log base 3 of x plus 4. I'm going to divide by 3. Negative 3, and I'm going to move this up because I need more space, and I get negative 2/3 equals log base 3 of x plus 4. Now I can curl it, and I get x plus 4 is equal to 3 to the negative 2/3. And then I could subtract the 4. I get x is equal to negative 4 plus 3 raised to the negative 2/3. And I went to my calculator, and I get negative 3.519. So negative 3.519 comma 0 is the x-intercept. And you can see they're about right. Maybe this one I'm off a little bit, but that one's not too bad. Okay, so for this one, my parent is going to be y equals the ln of x. Oops, went too far up. ln of x. Remember the base is e. So my points on this graph are going to be 1, 0, e comma 1, which is about 2.7 comma 1, and e squared comma 2. And that is about 7.4 comma 2. So my points on this graph are 1, 0, 2.7, comma 1, 7.4, comma 2, and this is the ln of x graph. Now I do see some transformations. I see an A, I see a C, I see a D, and it's A is going to be 2 times the y value, C is going to be right 1, and D is going to be up 3. Known as a right 1, x equals 1 is my vertical asymptote. So right here, x equals 1 is my VA. And then I'm going to do my transformations. Oops. Double the y. Doesn't do anything. Right 1, up 3 is right here. And that is the point 2, comma 3. This point right here at 2.7, comma 1. I can double it, which would be 2.7, comma 2. Right 1, up 3, which is right here. And that point is E plus 1, comma 5, which is about 3.7, comma 5. And technically that's enough for me to draw the graph, but I'm going to do this point right here at 7.4, comma 2, double it, 7.4, comma 4, right 1, up 3, 1, 2, 3. Have this point right here, and now I get this graph that looks like this. My domain is 1 to infinity. My range is all real numbers. And the right side of the graph goes up forever to infinity, and the right side of 1 goes down to negative infinity. So the hard part is knowing what your base is and making sure you're plotting a couple points on there. There's always going to be 1, comma 0 and base, comma 1 are your 2 points on the graph. Okay, so finally let's wrap it all up and talk about in general what these graphs look like, especially if you put a negative with some of these. So e to the x is a exponential growth graph, should look like this. One end levels off, the other side goes up to infinity. So if I did e to the infinity, it goes up to infinity. If I did e to the negative infinity, which is the left side of the graph, it levels off to 0. So what does the little negative sign do in front? This negative sign in front should make it flip over the y-axis. So the graph should be like this, and it's a decay graph now, because e to the negative x is really 1 over e to the x. So when I go over here and plug in infinity, and if we do e to the negative infinity, it levels off to 0, and e to the negative of negative infinity, which is e to infinity, which is the left side, it goes off to infinity. Let's talk about these two right here. Well, 1 over e to the infinity is equal to 1 over infinity, and 1 divided by a very, very big number is a really, really, really tiny number known as 0. We've talked about this before in this class. You should remember this. Okay, a log graph. The log graph is this little curly graph that goes through the point 1, 0. I don't need to know that. But the right side, so log of infinity goes up to infinity. The base is arbitrary. I don't care if the base is 2, 5, 8, e, 10. It doesn't matter. And then it says 0 from the right side, and the right side of this, so log of 0 from the right side is equal to negative infinity. Over here, what does this negative sign do here? This makes it flip over the x-axis, so now it's flipped upside down, and the graph kind of looks like this. So negative log of infinity is negative infinity, and negative log of 0 from the right is equal to infinity. So you could always try to plug in. So in summary, e to infinity is infinity, e to the negative infinity is 1 over e to the infinity, which is 1 over infinity, which is 0. E to the 0, anything to the 0 power is 1. Log of infinity is infinity. And log of 0 from the right side is negative infinity. These we should know from our basic graphs. So what I'm going to do is try to plug in these x values. So I see little x values underneath here that I'm going to plug in. So I'm going to make this a little bit bigger. I'm going to plug in infinity. I get e to the infinity. Well, I already said e to the infinity was infinity. Now it says plug in infinity here, so I get e to the negative infinity, which is 1 over e to the infinity, which is 1 over infinity, and I said 1 over infinity is 0. This one says plug in negative infinity, so it's e to the negative infinity parentheses squared. Negative infinity squared is positive infinity, and e to the infinity is infinity. I'm going to change my color. I'm going to plug in infinity here, so I get e to the 1 over infinity. Well, 1 over infinity is 0, so this is e to the 0. This is 1. Now I have to plug in 0 from the right. So it's e raised to the 1 over 0 from the plus side. So on the plus side of 0, that's a really small positive number. 1 divided by a really small positive number is a really big positive number. So that is just e to infinity, which is infinity. This next one I'm going to slide over a little bit. All these terms don't really matter. What I really only care about is this term here. So I get e to the negative x squared, and I plug in infinity, I get e to the negative infinity squared. Notice the negative is on the outside of the parentheses, so this is e to the negative infinity, which is 1 over e to the infinity, which we said was 0. Next one, I'm going to plug in infinity, I get e to the infinity minus 3. Well, e to infinity is infinity minus 3, and I'm pretty sure infinity minus 3 is still just infinity. This one's going to be e to the negative infinity, I think, plus 5, and I think I talk about e to the negative infinity just being 0 plus 5, so this is 5. And then again, this turns out to be 4 minus e to the negative infinity squared, which is 4 minus e to the infinity, which is 4 minus infinity, which is negative infinity. I'm going to move this up a little bit. Use pink. Plug in infinity. The base doesn't matter. Log of infinity is infinity. Again, the base doesn't matter. So this is negative log of negative infinity, which is negative log of infinity, which is negative infinity. And this is the natural log of 0 from the right side. And on the right side of 0, the graph goes down to negative infinity. And finally, I do this last row. Plug in this, I get 7 plus log of infinity, which is 7 plus infinity, and that's still infinity. I get 3 minus log of infinity, which is 3 minus infinity, which is negative infinity. And now when I do this last one, this is the natural log of 4 from the right minus 4. Well, something that's a little bit bigger than 4, minus 4, is something that's just a little bit bigger than 0. And we already said that the log of 0 from the right side is negative infinity. Okay, there you go.